So the interesting part of what we're talking about in this session is not just what vector-valued functions are, but specifically how to do calculus on them. So how can we differentiate and integrate vector-valued functions? The nice thing for us is everything still comes back to limits, and limits are still super friendly, even on vectors and even in three-dimensional space. So we won't go through all the details of like deriving all the formulas, but really all that you need to know is when someone gives you a vector valued function and asks you to do something like differentiate or integrate, you'll just do it to each component. It's basically like best case scenario of what you would hope that you could do with vectors. So you just do it to the x component, the y component, and the z component, if, for example, it's a three-dimensional vector. Also, you'll notice, you probably would have assumed this anyway, but all of the normal rules of differentiation still apply to vectors. So for example, you'll notice this is a bold C, because what I mean is that maybe we're differentiating like a constant vector. I don't know. There's a constant vector. It's a bold C because it's still a vector. But if you differentiate a constant vector, it still gives you 0, although this 0 is bold, because what I really mean is it gives you the 0 vector. But differentiating a constant still gives you 0 just in vector form. If someone puts a constant in front of a vector, like I'm using a k here instead of a c, I don't know why, instead of changing anything that you're doing with differentiation there, you just pull the constant out to the front just like you would with a normal function in single variable calculus. Addition and subtraction works the same way. So if you're differentiating two vectors added together, you just differentiate the first one and differentiate the second one. Nothing goes wrong with addition or subtraction. The place that things will get interesting, as it does sort of in single variable calculus as well, is when you start multiplying vectors together and differentiating those. So in single variable calculus, we have things like the product rule, which is basically what this is saying here. So one thing to note, the product rule might be a little bit different than what you're used to seeing here, because I'm multiplying together a function and a vector, which is basically what we knew how to do before we talked about things like the dot product and the cross product. I knew how to multiply something like a number or a function into a vector. So you're just like distributing the function into each component of the vector. This is not too terrible. And when we differentiate a function times a vector, we use the regular old product rule. So we can think just the left part, d right. Now, derivative of the right in this case is still derivative of a vector, but you're just differentiating component. So left d right plus right, the regular old vector, d left. D left in this case is the derivative of the function, just like you know how to normally differentiate. There's no changes there. So this is just our regular old product rule, but in this case we have a function times a vector, but nothing changes. So that's super nice about not having to like remember a new rule there. Now, one thing that is sort of important for us to observe here is the derivative of a vector valued function gives us a vector, which I guess we kind of saw that just a second ago. When you differentiate a vector valued function, you're just differentiating component. So the derivative of a vector, this is the derivative of a vector, is itself another vector. So we might think about what does that look like on a graph. Now, a vector valued function is just going to be some sort of a curve traced out where every single point on the curve is a vector value. So here's some point on our vector valued function, like this would be another point on our vector valued function over here, but wherever our vector ends, that gives us another point. So as you sort of scroll through values on your vector function, it sort of traces out some curve. Now the tangent to this function is, or sorry, the derivative of this vector is just like what you're used to seeing, the tangent of our vector valued function. So it's this tangent vector going this way. Now, the magnitude of this tangent vector sort of depends on how fast you would be scrolling through this vector valued function. So as you scroll through t values, if this function gets traced out really, really, really fast, that would correspond to a larger magnitude tangent vector. If you scroll through t values and it traces out this function really, really, really slowly, that would give you a smaller magnitude tangent vector. But whatever direction you're tracing out this vector valued function, that's the direction of your tangent vector. In just a few minutes, we're going to start normalizing these tangent vectors, meaning I don't really care how fast we're traveling along this curve. I'm going to make the magnitude of this tangent vector equal to 1. I'm going to make it a unit vector, but for right now, the tangent vector is just sort of tracing out the direction that we're traveling along this vector valued curve. Same thing happens in 3 space. So one of the curves that we saw at the beginning here was sort of like a helix that was coming this way. So our tangent vector on this helix would be doing things like this way, and just kind of however you're traveling along this helix function. Our tangent vectors would be just traveling sort of all the way off, I don't know how to say it without using the word tangent, but traveling tangent to this helix. But it works the same in 3 space as well. Now, so one thing to note here is in regular single variable calculus, we're used to the derivative being useful because it gives us the slope of the tangent line. Now, in this case, when we're dealing with vector valued functions, it doesn't exactly give us the tangent line, it gives us a tangent vector. So it is important to note that using that tangent vector, we can still get the equation of the tangent line. We just have to do a little bit more work. So what we say in this case is that R is going to be defined as, R is going to be our tangent line. And then R sub 0 is basically our point of tangency. So this is our point of tangency. And I'll draw all this stuff in just a second. And then V sub 0 is our tangent vector. So I'll show you how all this works. Let's think about just some arbitrary function. Let's see, I'm going to just kind of draw something sort of friendly like this. There's a vector valued function. Now, first, in order to define the tangent line, I need to define a point. So I'm going to start with some chosen vector, and I'm going to call this vector, let's see, I'm going to call this vector R sub 0. This is like my starting point vector. So here's my point of tangency on my vector valued function. This is that R sub 0. Now from that point of tangency, I know that I can get, oops, I wanted to switch colors. I know that I can get a tangent vector, and I'm going to call that vector V sub 0. The sub 0 is just because I have sort of locked this at a point. If I just said V, it would be telling me that I could that V could vary, but since I say V sub 0, I just mean it's locked at this point of tangency. So there's my tangent vector, and then in order to get the equation of the tangent line, what I'm trying to do is basically just like extend this vector out in both directions. So to do that, I use this component t, which is basically saying I can take this vector and multiply it by whatever I want. I can multiply it by something positive, which would make it larger this way. I can multiply it by something negative, which would send it out this way. But I can multiply it by whatever I want. And as long as I'm starting that vector at this initial point of tangency, which I am, and then extending it as far as I want in either direction with this t value, I'm defining a tangent line, which is what this little r is. That's the equation of our tangent line. So your starting point plus really anything times your tangent vector gives you the equation of the tangent line. And that's in two-dimensional space. You can do the same thing in 3 space as well. Let's see, let me draw, well, I guess I don't really need to. You can do the same thing in 3 space as well. It's just like a little bit harder to draw on a sheet of paper, but same thing. So you have your starting point, and then you just extend your tangent vector as much as possible in both directions. Okay, so using that, let's actually do an example and find the equation of the tangent line to this circular helix. So a couple things. We are not fixing this at any particular point. This is just sort of like some general starting point. So I'm not saying any particular t value. I'm just saying let's fix it at t sub 0. So remember, the formula says the equation of our tangent line equals our starting point plus really anything times our tangent vector. So our starting point plus some t value times our tangent vector. This t value is going to stay the way that it is. So I guess the first thing that I need to do is find my starting point. So this is basically saying to find your starting point, just plug in t sub 0 wherever you see a t. So my starting point would be cosine of t sub 0, or t naught, and then sine of t naught, and then, oops, just t naught. So there's my starting point. Now who knows where this is, because I don't have any specific value for t sub 0, but this is so that we could really plug anything into this later. Now I need a tangent vector. So in order to get a tangent vector to this particular point, I'm just going to differentiate component, component, component. So the derivative of cosine of t sub 0 is negative sine, evaluated at that same point. Derivative of sine is positive cosine, evaluated at that same point. And then the derivative here of just t, and then evaluated at t sub 0 is just 1. So there's our tangent vector. And the equation of the tangent line then is just this starting point plus really any multiple of this tangent vector. So this guy plus any multiple of our tangent vector. So let's add those two together. So I'm going to have my starting point, so cosine of t sub 0, sine t sub 0, and then just regular old t sub 0, and then plus, now I'm going to multiply each of these components by t, because I really want to have any multiple of my tangent vector. So then I'm going to add, let's see, negative t sine of t sub 0, t times cosine of t sub 0, and then t times 1, so just like that. And my answer gives me a new vector valued function, which is a tangent line. So I have, oh, this is going to be kind of long. Cosine of t sub 0 minus t sine of t sub 0. First component is right there. Now t is my variable here, so I would never plug anything in for t, because that's what actually allows this line to sort of extend forever in both directions. My second component is sine of t sub 0 plus t cosine t sub 0. And my third component is just t plus t sub 0, and then I'll close that off. Now t sub 0 is the actual fixed value that you would plug in depending on where you wanted to start on your graph. T is the variable, so t sub 0 is fixed, t is the one that's going to vary to actually make this a line. But that's the equation of our tangent line, and then you can actually plug in some point and make this specific, which I don't think we're doing in this example. But you could. Okay, so here's another application now that we're able to find the equations of the tangent lines. So this one says the graphs of this first vector valued function with an inverse tangent, which might freak you out a little bit. So inverse tangent of t, sine of t, and then t squared, and then a second vector valued function, t squared minus t, and then 2t minus 2, and then ln of t. These two vector valued functions intersect at the origin, so that's just given to us. Find the degree measure of the angle between their tangent lines at the origin. So if you can imagine, these are curvy functions, so we might have something going like that, and our job is to find the angle of intersection, but you can't really define an angle when you have curvy functions. So what we'll do instead is talk about what is the angle between their tangent vectors or their tangent lines. So in order to do this, really I think all that we need to do is find their tangent vectors at the point 0, 0, 0. So let's see. There is one little extra challenge here. I'm saying at the point 0, 0, 0, but I don't really know what t is, what our parameter is that makes this vector value 0, 0, 0. So maybe that's like one first thing to think about. So let's find the derivative of this first vector. Now you can differentiate inverse tangent. So one thing that you might want to do is pause the video right now and actually on a sheet of scratch paper or on your notes, differentiate inverse tangent, and then we'll start this back up in a second. So hopefully you've differentiated inverse tangent. The derivative of that is 1 over 1 plus t squared, but you should verify that because it is really good practice to be able to remember how to differentiate inverse functions, especially inverse trig functions and interesting things like that. So 1 over 1 plus t squared, derivative of sine t is cosine of t, and then our last component is 2t. So there's our derivative of our very first vector. Now, one thing I would want to know is, as I said a second ago, what is our t value when our vector, our first vector, is actually equal to 0, 0, 0. So what value of the parameter passes us through the origin? Now, this one's actually pretty friendly because of this third component. The only way that this third component is going to be 0 is when t equals 0. So I can actually answer this question right away. T has to be 0. And you can verify also sine of 0 is going to give us our second component of 0, and inverse tangent of 0 is also 0. So our parameter value t equals 0 is what gives us the origin here. And because of that, what I would like to do on this tangent vector is not just find a function for a tangent vector. I would specifically like to find the value of this tangent vector, the particular vector at t equals 0, because that's going to be the tangent vector to the function at the origin. So when I plug in t equals 0 into everything here, I'm going to get a first component of 1, a second component of 1, and a third component of 0. So there's my tangent vector to this graph, this vector valued function at the origin. It's 1, 1, 0. Now let's do the same thing for our second vector. So first of all, let's see. This one, before I even differentiate or anything, this one is at the origin when t equals what? So I'm just going to choose one of these components and think about which is the easiest component to solve. The first and second component are both pretty easy to solve, so is the third one really. But let's see, I'm going to set the second component equal to 0, and I find when t equals 1. So t equals 1 is the parameter value that's going to make my vector value equal to 0, 0, 0. So now that I know that, let's differentiate this vector. And my first component when I differentiate is going to be 2t minus 1. My second component is just 2, and then the derivative of my ln of t is 1 over t. So here's my derivative vector. Now this is just a new vector valued function that would give me the tangent vector at any t value that I plug in. Specifically, I want to find the vector, the tangent vector when t equals 1. So when I evaluate this thing at t equals 1, I find specifically a tangent vector of, let's see, 2 minus 1 is 1, and then 2 and 1. So there's my tangent vector at the origin. I could graph these things on a three-dimensional space, but I won't, kind of because I don't even really need to do that in order to find the value of the angle between these vectors. So remember from last time, if I want to find the angle between the vectors, I can use the dot product. So one thing that I know is when I use the dot product, my first vector was what? My first vector was 1, 1, 0, I think. If I do 1, 1, 0 dotted with the second vector of 1, 2, 1, the formula says the dot product of those two vectors equals the magnitudes of both of the vectors. So the magnitude of the first one times the magnitude of the second one. Oops. The magnitude of the second one times cosine of the angle between them. This is like one of those really, really useful things about the dot product. Because remember, the dot product is actually really easy to compute. The dot product is the one where you just do component times component plus component times component plus component times component. So 1 times 1 is 1 plus, and now we'll do second times second, so 1 times 2 is 2, and then plus third times third, which is 0. And it's nice that the dot product is that easy because it's kind of so useful for finding the angle between these things. Now we just need to find the magnitude of the first vector. So the magnitude is just where you square each component and then add them together and take the square root. So this is going to be the square root of 1 squared plus 1 squared, so plus 0 squared. I'm writing this all out even though you probably don't need me to, but I am anyway. Times the magnitude of the second component, so 1 squared plus 2 squared is 4 plus another 1, and then all of that times cosine of theta, and I'm trying to use this formula to find theta. Like that's my whole goal. So the left side of the equation is just 3 equals, what do we have, square root of 2 times 1, so square root of 6 times cosine of theta. Now all of this simplifies a little bit to 2 square root of 3 cosine of theta, and then I really get 3 over 2 root 3 equals cosine of theta. And I think, I can't remember what I said in the problem. Did I say find the degree? Yeah, find the degree measure of the angle between their tangent lines. So this is actually a pretty friendly angle. I can simplify this even more and say cosine of theta equals, well, 3 is the same as square root of 3 times square root of 3. So I can cancel here and here, and I really get cosine of theta equals square root of 3 over 2, which tells me that theta has to be 30 degrees. Theta equals 30 degrees. I guess actually there's another cosine value that would give you an angle between the vectors. I think I might have left it out of the problem, but another way to say this would have been find the degree measure of the acute angle between their tangent lines, because the other angle here would be the obtuse angle between those vectors. But let's just pay attention to the smaller angle. So theta between those two vectors is 30 degrees, and we just use the dot product for that. So now that we've gone over dot product again, it's kind of a good time to think about how does differentiation work with these new forms of multiplication that we defined last time. So last time we talked about the dot product and the cross product, and that was sort of like our new information from the lesson from last time. Now remember, with differentiation we have this thing called the product rule, and I actually rewrote this in today's notes because now we're dealing with a function multiplied by a vector. And it's the same as what you always knew the product rule to be, so left d right plus right d left, even though maybe d right in this case means derivative of a vector, even though d left means derivative of a function. So it turns out there's also a product rule for the dot product, and there's another product rule for the cross product, which might sound a little bit overwhelming, except that it's exactly the same as the original product rule. So one thing that we never thought about with the original product rule is that there's this multiplication going on between this first function and the second function, or in this case the vector and the function. This is multiplication. That multiplication came from the fact that we were doing a product rule for multiplication. So to sort of change this around for the dot product, this multiplication is just going to change to a dot. And then same thing, to change this to a product rule for the cross product, this multiplication is going to turn into cross product. So let's see how this works. In this case, we have two vectors, r and s, and I'm dotting these two together. So I'm doing r of t dot s of t, the dot product of these two vectors. If I want to differentiate those, it's basically the same as the original product rule, except this dot is going to turn into the dot product. So I'm going to go left dot d right, so r dot s prime, plus right dot d left. So same as the original product rule, left d right plus right d left, except the operation between them, instead of just regular old multiplication, now is the dot product. And same thing for the cross product. So I'm going to go left cross, d right plus right cross d left. And there's our product rule for the cross product. So I guess it sounds a little bit intimidating because it is two more product rules, but it's exactly the same as the product rule that you already know. So really not too bad. And then I'll leave it to you in the exercises to practice those new product rules. Also, I mean, one thing that we've seen so far is that differentiation with vectors is pretty friendly. It's kind of just component by component. Integration is same thing. So everything is component-wise with integration, just as what you would hope for it to be. So here's an example of a 3-component vector, t squared e raised to the t and then -2 cosine of pi t. We're going to do two examples here. First, finding a definite integral, so integral from 0 to 1, and then we'll do a different example with an indefinite integral, just to talk about what the plus c means when we're dealing with vectors. So I'm just going to integrate this component by component. So this is the integral from 0 to 1 of t squared dt, that's my first component. The integral from 0 to 1 of e to the t, is my second component, and then the third component, integral from 0 to 1 of -2 cosine of pi t dt, just component by component. So not too bad, which is, I don't know, it's always nice when this is like sort of what you would expect for it to be. When you get your final answer here, we're going to do t cubed over 3 evaluated from 0 to 1 as our first component, e to the t evaluated from 0 to 1 for our second component, and then -2 over pi sine of pi t evaluated from 0 to 1 for our third component. And when you actually evaluate those, which if you want to pause the video now and evaluate them, you can do so, our answer is 1/3 and e minus 1 for our second component, and I believe the third component is just 0, but you should verify that. So we came out with just a vector answer for our definite integral. The indefinite integral is going to be just a little bit different because remember, when you're dealing in single variable calculus with indefinite integrals, you have a plus c that you have to deal with. And we'll have the same thing here, except plus c isn't going to mean a number. Plus c is going to be some constant vector that we could find if we were given an initial value, which we will be given on the next example. So let's start this. Component by component, this is only a 2-component vector. So I'm going to integrate 2t dt for my first component, and I'm going to use vector notation with the I and the j here on this one, plus the integral of 3t squared dt times our second component j. So the integral of 2t is going to be 2t squared over 2, so in other words just t squared, times I, plus, and then 3t squared is just going to be t cubed times j. So that's a nice answer, except we're not done because this is an indefinite integral. So what I need to do is put a plus c, and I'm actually not done with this. Right now this is incorrect because plus c, the way that I have it written, c would be just some constant. What I need to do is put vector notation over it to make it clear that this is a vector. So my answer really in other notation could look like this: t squared, t cubed, plus some constant vector. Now a constant vector doesn't have to have identical components. Like this vector, for example, is a constant vector. It just doesn't have any variables in it. So I don't know what this is, and I can't solve for it because I don't have an initial condition in this particular example, but I do have to put a plus c, plus vector c, if I'm dealing with indefinite integrals with vectors. So the only way that I can solve for the plus c is if I'm given an initial condition. So I am, in this case, this is sort of like a differential equation with in vector form. So if I'm given the derivative, this is the derivative vector, and I'm given an initial condition, all the rules of single variable calculus still apply. So if I want to get to my original vector and I'm given the derivative, I need to sort of undo differentiation, and I still do that with integration. So I'm going to go indefinite integral of r prime dt, which is going to give me r of t, and then I am going to have some constant, so I'll have to figure this out. But let's start. So let's integrate my r prime with respect to t, and when I do that, I get this vector. Let's see, my first component is 3t, and my second component is t squared. and I have plus some constant vector because this was an indefinite integral to begin with. So the only way that I can find the constant vector, all of this stuff that I'm finding here is r of t, the vector r of t. The only way that I can find the constant vector is if I'm given some initial condition, which I am. So I know that r of 1 is 2, 5. So I know that when I plug in 1 here, oops, not like that. When I plug in 1 here, and I have plus some constant vector, I need to get to 5 according to my initial condition. So that tells me that 3 plus the first component of my constant vector has to equal 2, and then 1 plus the second component of my constant vector has to equal 5. So I can tell that my constant vector has to be -1, 4. And putting all of that together, my final answer, r of t, is 3t, and I'm just going to put my constant vector into each component. So 3t minus 1, rather than writing the plus -1, 4 over here, I'm just going to put it into this component. So 3t minus 1, and then t squared plus 4. And now I don't have a plus c because I already solved for it. So differentiation and integration are both pretty standard. Even with vector valued functions, I think it's nice to see a couple of examples, but everything works out really nicely. We have our new product rule, which isn't really new, but sort of an analogous product rule for dot product and cross product. And at this point, if you want to go on to the exercises, you can do sort of the bulk of them. A lot of these are just practicing kind of differentiating vectors, and sketching vectors and their derivatives. So sketching vectors and their tangent vectors, including in 3 space in number 7. Let's see, this should go all the way up to number 14. So number 8, finding tangent lines using that formula that we found. Number 9 is using the new product rule for dot product and cross product. And I think numbers 10 through maybe 12 are using integration. Now numbers 13 and 14 I think are some of the most challenging problems in this whole set. So this is verifying formulas. You'll notice in the solutions that are on the very last page of your notes, there are no solutions for these because there are a whole bunch of different ways to do these problems, but just go back to basics and use the formulas that you know from last week and this week. Like use what you know about the cross product and use what you know about the dot product. So you should be able to verify both of those formulas. But these might be some good ones to go over in office hours this week. So if you want to start on those exercises now, you can get through number 14 with the part of the video or the part of the lesson that we've gotten through now. Or you can go on to part 3 of the video and finish out talking about tangent and normal and binormal vectors.